exponential growth occurs when a quantity increases by the same percent over equal time periods. And this can be modeled by the exponential function in which you learned in the first part of this lesson, y equals a times b to the x power, where a is greater than 0 and b is also greater than 0. Okay. To find the amount to which the quantity grows after t time periods, we can use this model called the exponential growth model, where y equals a times the sum of 1 plus r to the t power. Let me define what every single variable means here. A will be the initial amount that you begin with. 1 plus r is known as the growth factor, and r is the growth rate. It would usually be a percentage that's given to you, and t would be the time period, and usually it's in years. To prove why this model works, we can begin with the initial amount, and the amount of increases would just be taking the initial amount, a, and multiplying by the growth rate, r. And when we factor out a, we get 1 plus r. A times 1 is a times r gives you this part. So this is where we have this formula. So you must be wondering where the t comes from. Well, for the first year, or the start of the year, the growth factor would just be 1 plus r to the first power times a. And for the second year, you would take what you have from the previous year, and then you need to multiply by another growth factor, 1 plus r to the first power. So therefore, by using the product property, 1 plus 1 will give you 2. And therefore, for t years, we would get the formula y equals a times the sum of 1 plus r to the t power. Therefore, y is the growth after t years. A very common real-life example that is used for this exponential growth model is calculating compound interest. The interest earned on both an initial investment and on previously earned interest can be modeled by an exponential growth model. So this will be the same. A will be the amount that you invest in the beginning. Initial means the beginning. And R will be the annual interest. Annual means yearly. And T will be the number of years. So where does this compound interest come from? Let's say I deposit $50, the principal, okay, the beginning amount, into a savings account that earns 2% interest compounded annually. This just means interest that's earned on both the principal and any previous earned interest. So this table shows the balance of your account after 3 years. You began with $50, and by substituting in 2% into the formula and the principal of $50 as your A, you would get 50 times the sum of 1 plus 0.02 to the first power. And after 2 years, it would be to the second power. After 3 years, it would be to the third power. And by using this formula, it also suggests a compound interest formula compounded yearly. So the balance y would equal to the principal times the sum of 1 plus the annual interest rate to the time in years. So this exponential growth model can be rewritten as capitalized A, which stands for the amount that you earned on your principal and any previous earned interest, and I will set it equal to capitalized P, which stands for the principal, the amount that you first put in the savings account, and the growth factor will stay the same, and it will be to the T power in years. So to finish this problem, I would substitute $50 in for P, 2% in for R, and because I ended with 3 years, I'm going to take this to the third power, and you may use a calculator to obtain this amount. And if the interest is compounded in times, example, monthly, a year, then the compound interest formula will be given by A equals P times the sum of 1 plus R over N to the N times T power. I will explain a little further about what this formula means later. Okay, let's continue with the guided practice. If the population quadruples each year, what is the population's growth rate as a percent? Explain. Well, the growth factor is 1 plus R, according to the model that I just explained. Y equals A times 1 plus R to the T power. And we need to set this equal to 4 because the population quadrupled. And then to solve for R, it would be 3. So an example will be a growth rate of 300% would create a growth factor of 1 plus 3 equal to 4, which would represent the quadrupling of the population every year. Word problems. I'm going to show you a typical exponential growth modeled word problem. In 1830, the population of the U.S. was about 12 million. By 1890, the population was 62 million. Assume the population growth from 1830 and 1890 was exponential. So they tell you directly that you need to use the exponential function. Part A, write an exponential model for the U.S. population from 1830 to 1890. So first, I'm given 2 points. In 1830, I can represent that as year 0. And then I will have 12 million people in the beginning. And 60 years later, I take 1830 and I'm going to subtract that from 1890 to get 60. And in 60 years later, you have 62 million. Okay, so I'm going to take the exponential growth function, a times b to the x power. I'm going to substitute in some numbers. Well, I'm going to use this point, 12 million for y, a times b to the 0 power. Therefore, a is 12 million. And then I can use this model again and substitute this point, 62 million equals 12 million can substitute 60 here. Okay, then I can cancel out all my zeros. And then my next step will be to write 62 equals 12b to the 60 power. And then I can take 62 divide by 12. I'm going to write it right here. And let that equal to b to the 60th power. I can simplify this, and this becomes 31 over 6. Okay, and then to solve this, I need to take the radicand to the 60th root. So that's a technique I haven't taught you yet. So again, you can just use a calculator, and B will be about 1.03. And on the test, I would give you something that you will not need the calculator to find out what B is. And part B, by what percent did the population grow per year from 1830 to 1890? So since B is about 1.03, we can say that the growth factor is equal to 1 plus 0.03. So therefore, we have to read this as 3%. So this is the answer for part B, and this is the answer for part A. Now I'm going to show you how to use the compound interest formula. You deposit $1,000 in an account that pays 3% annual interest. Find the balance after 8 years if the interest is compounded annually, meaning every year, quarterly, every 4 months, monthly, weekly, and daily. For annually, we can substitute 1,000, which is the initial deposit, in for P. And we can multiply that by the growth factor of 1 plus 3%, which is 0.03. And it's compounded annually, so I just need to divide that by 1 for 1 year. And I'm going to put that to the power of 1 times 8 years, because you're going to do this for 8 years. And then we could simplify this. And of course, I'm not going to ask you to multiply this by hand. You can go ahead and use the calculator to obtain 1,266.77 as your new balance after 8 years. And I would like to say that whenever you calculate the balance for something that's compounded annually, you can go ahead and use a more simplified formula. A equals the principal times the growth factor, 1 plus the rate, to the t power, where t is the number of years. Okay, because when it's compounded annually, n is obviously 1, and it won't matter. Okay, you can go ahead and cancel that out. But it will matter if you have something that's compounded quarterly, okay? When something is compounded quarterly, let's say $1,000, 1 plus the rate of 3%, 0.03, I need to divide that by 4, because within that year, in every 4 months, the balance of $1,000 will be compounded, and you'll definitely earn more money. So I'm going to take this growth factor and put it to the power of 4, representing the quarterly, times 8. So the 4 corresponds to N, and the 8 corresponds to T for the number of years. And after you calculate this, or after you use the calculator, you should get an amount of $1,270.11. And you would do the same thing for the next one. So the balance equal to $1,000, 1 plus, and it's going to be monthly this time, so 3% divided by 12, and we're going to take the growth factor and put it to the power of 12 times 8. And the amount earned after 8 years compounded monthly would be $1,270.87. So you can see the increase of a couple of cents. And I'm going to do the same thing for the rest of the 2 problems. Balance equals $1,000 times growth factor, 1 plus 3% over 52 weeks, because there's 52 weeks in a year, and we're going to do this for 8 years again, so 52 times 8, and you should get $1,271.16. As you can see, the amount of money has increased between monthly and weekly. And if you were to compound the amount of deposit daily, you'll definitely earn a little bit more. So again, I would take the principal of $1,000 and add this to the growth factor, 1 plus 3% over 365, because there's 365 days in a year. And we're going to take this to the power of 365 times 8 years. So this is the power right here. And after using the calculator, you should get a new balance of $1,271.24. So again, there's a slight increase between weekly and daily when the deposit is being compounded. The following chart will help you understand what happens to the growth factor 1 plus R after being compounded with an interest rate of 100% after 1 year. So if the interest rate is 100%, then your R is 1. So that's why every one of these, the numerator here, are all 1. And the denominator changes because it's being compounded yearly and then semi-annually, quarterly, monthly, and so forth. And the exponents changes with the denominator. I want you to see this pattern here. And because this is for 1 year, we don't need to take, for example, the 1 here in the exponent and multiply it by 1, because it's still 1. And same thing for 2. It's 2 times 1 is still 2. Okay, so don't worry about memorizing this. I just would like you to understand what you're supposed to put in the denominator when I say, or when I give you a problem that asks you to calculate the amount earned when something is when a deposit is compounded quarterly, for example. Okay? And this concludes the lesson.